Hi everyone, welcome back. Today we're going to be looking at the chain rule. And we need to look at a particular process for when we're taking derivatives to, again, try to streamline that whole derivative taking process. And in order to do this, we still need a few more techniques, and this is one of those techniques where we're going to be talking about this chain rule. Now, when we talk about the chain rule applies when we're looking at function composition. All right, when we're trying to take a derivative and we see a composite function denoted as f of g of x, if we can identify that we have a function composition when we're going to take a derivative, then that means that we're going to be able to apply the chain rule for derivatives. The chain rule states that if g is differentiable at x and f is differentiable at g, then the composite function f of g is going to be defined by f of g of x. And this is going to be differentiable at x, and if f prime is given by the product, f prime of x is equal to lowercase f prime of g of x multiplied by g prime of x, then we have that differentiable function, therefore we're going to be able to take the derivative. So what we want to see here is we want to start extracting this chain rule, and we want to know how to work with it. And what I'm going to say here is let's talk about a different view for this chain rule. What if we make a substitution for u is equal to g of x? In other words, identify an inside function. Then when we identify that inside function and we want to take the derivative of the whole overall function, this function composition, capital F, then what's going to happen is we have to take the derivative of all individual functions that were made of that function composition. In other words, we have to take the derivative of that u function with respect to x, and that's where this portion comes in, and I'm circling this portion here, taking the derivative of u of the function u with respect to x. And then we also get to take the function of y with respect to x as well, or in this case with respect to u, because when we made the substitution we said that y was a function of u, and that's where this comes in. And so when we're looking at the chain rule, we always have to account for all of the different embedded functions that we can account for. So let me direct you to this overall example. What if I say that I wanted to consider this function y to be equal to 3x plus 5 quantity squared? And what if I then said find y prime? In other words, the derivative. Well, according to our techniques so far, the technique so far would say that first we would need to expand this binomial, which means we would get 9x squared plus 30x plus 25. And now since that binomial is in polynomial form, we can then just take the derivative term by term, applying all the rules that we've learned so far, which means that y prime would be 18x plus 30, and then the derivative of 25 would just be 0. So looking at this derivative, wow, that derivative is nice. However, we can rewrite that derivative differently. And the way that I'm going to rewrite this derivative is going to be in this manner, that I want to take y prime and I'm going to decompose y prime. Now, you might not have to do this as we work through a lot of these derivatives. However, I'm doing this so that we can illustrate what was taking place. Now, I decompose y prime into 2 times the quantity of 3x plus 5 multiplied by 3. Now, if you redistribute everything, you're going to find out that it's the same y prime of 18x plus 30. And the reason I want to do this is because this is going to outline that chain rule process. Okay, so what I want to see now is going to be the derivative of the outside function. Okay, so what is the outside function? Well, the outside function here is going to be this piece. This is my outside function. Which means when I take the derivative of my outside function, well, according to our derivative rules, we drop the exponent forward and we take 1 away from that exponent. And that's what this piece is here. And I will highlight that as well. There we are. That's that piece. Which means this is the derivative of the outside function. Now the 3, we have to account for that 3. So where the 3 comes from, as we can see from the chain rule at the top of our screen, this is going to come from the derivative of some inside function. So what we then need to do is we need to identify what is that inside function. And so what I'm going to do here is I'm going to identify that. I'm going to identify this piece as 3x minus 5. This is going to be our inside function. Which means when we take the derivatives, we still need to account for the derivative of that inside function. And that's at du dx at the top of your screen here. Let me move this up just a little bit. There we go. And so that's at du dx. So the derivative of the inside function, that's this number 3. And that's a derivative of the inside function. Now, why do we want to break this off into these different pieces? Well, the reasoning behind this is that we can now start talking about more complicated derivatives other than just polynomials, and we can start implementing this chain rule, and that way we can take derivatives at a much faster rate. So what is that then going to look like? Well, we're going to keep track of everything that we do, and we're going to keep track as that inside function, outside function, derivative of the inside function, so on and so forth. So for this example, we're going through and we're going to find the derivative. So for part A, I want to work with f of x is equal to 1 plus x squared to the power of 99. Now again, you're going to look at this and you're going to say, oh wow, does Mr. Castro really want me to expand this 99 times or 98 times? The answer to that is going to be no, we don't want to do that expansion. However, we can still take this derivative by applying the chain rule. We're going to apply the chain rule to say, okay, well, you know what? We have an outside function. So this is my outside function. And I will need to take the derivative of that outside function. So the big key takeaway here is that we can do this, and we're going to apply that chain rule. Okay, well, what's the derivative here? Well, let me go with the power rule here. I'm going to take the derivative of the outside function, which means I drop the exponent forward. So that's 99 multiplied by, and in this particular case, the inside function does not change. So look at the example that we did before. Notice how the example before, inside of the parentheses for that 3x plus 5, it didn't change. It stayed as 3x plus 5. So your inside function, when you're working with the derivative of the outside function, should not change. This means that my inside function stays exactly as is. And we subtract 1 from the exponent to get us an exponent of 98. Now we need to multiply by the derivative of the inside function. And that's where this comes in now. So the inside function. Now, for the derivative of the inside function, we now just need to multiply by that derivative. So you can go through your differentiation techniques and now find the derivative of that inside function. Well, what's the derivative of this inside function? Well, the derivative of 1 is 0, the derivative of x is 1, and the derivative of x squared is 2x. And there you are. This is f prime. This is your derivative for that function. And again, we did not expand this function at all. And this is what the chain rule does. It allows us to bypass certain properties, and it allows us to focus more independently on these particular derivatives, where we have to then take a derivative of a function composition, which can turn out nicely. Let's look at part B. We want to work with g of x, which is going to be equal to 2 minus sine of x to the power of 3/2. So again, as we look at this derivative, I'm going to say, okay, well, I don't see any, let's say, products, because I'm not going to be using the product rule. I don't see any quotients, so I'm not going to be using the quotient rule. However, I do see a function composition. There is a big outer function, which I'm going to label as my outside function. And there is an inside function, which I will label. That inside function is this 2 minus sine of x. So that's your inside function. So in order to take this derivative, what we're going to do is we're going to take the derivative of the outside function first. And you're going to notice the outside function, that's just a nice power rule. So when we take that derivative for the outside function, you take the exponent, you drop it forward, you keep everything inside of that function the same. So 2 minus sine of x. Subtract 1 from the exponent. 3/2 minus 1 should get you 1/2. And then we multiply by the derivative of the inside function. Well, the derivative of the inside function, the derivative of 2 is 0. The derivative of negative sine of x is going to be negative cosine of x, which means this is my derivative. All I have to do is clean it up just a little bit more. G prime of x is going to be equal to negative 3/2 multiplied by cosine of x, negative 3/2 multiplied by cosine of x, multiplied by the square root of 2 minus sine of x. There we are. And there's g prime. Again, we didn't need to spend a lot of time figuring out what is this function as we, let's say, distribute or try to take square roots or anything like that. We can go simply straight into the chain rule. And this is one of those techniques that needs to follow you throughout the different courses that you're going to be taking for calculus, because this is one of those important ones, along with the product rule and the product rule and the quotient rule, that appears quite often throughout the rest of your math classes that you take. So let's see if we can start experimenting and making these a little bit more interesting. Okay, so one of the first ones that I want to take here, so on this example, we want to find the derivative part A. we're going to be working with y is equal to sine of 1 plus x squared, and this is going to have a square root. All right, so here we go. Again, we're now going to identify that we do have function composition. However, we're going to be ready for this. And we're going to be ready for this because this function composition uses 3 different functions. And we're going to outline those. Okay, so let's go ahead and let's rewrite this differently. I'm going to rewrite this as y, is equal to sine of 1 plus x squared, all this to the power of 1/2. Now, the big outside function, that's this big function to the power of 1/2. So this is your outside function. So what's your inside function? Well, that inside function and I'm going to say 1 is this one, sine of the quantity of 1 plus x squared. And then we still have another function inside of that one, so we have another function here. This function is going to be your inside function, part 2. So we have 3 different function compositions that we then have to worry about. Okay, so a lot of times what I tell my students is this: try not to worry about the inside function, the innermost function. In other words, inside function composition 2. Try not to worry about that one too much. Okay, we know we're going to have it, but we'll just kind of pin it and we'll put it in the back for now. So what I'm going to do is I'm just going to backtrack really quick, and I'm only going to focus on these 2 functions. And again, it's kind of like an onion. You got to peel it back layer by layer. If you look at it all at once, it'll get a little bit complicated. And so again, we want to avoid all of those complications. So let's see here. I want to find y prime, and I know I'm going to have to use a chain rule, which means I'm going to have to take the derivative of the outside function. That derivative for the outside function, we drop the exponent forward, we keep the inside function the same, so that's sine of 1 plus x squared, and we subtract 1 from the exponent, which means we're at negative 1/2, and then we take the derivative of the inside function. Now, you're going to notice what I'm doing here is I'm just denoting that we are going to take a derivative of that inside function. I'm not taking the derivative just yet. And the reason why I'm not taking the derivative just yet is because, again, I want to identify that I do have 2 different functions here. Okay, so what I'm going to identify now is this, that as I'm taking this new derivative, I now, inside of this function, have a new function composition. So again, I'm looking at the outside function, and I'm also looking at an inside function. And let's go with color gold here. Nope, that doesn't look too well. So let's go with color purple here. So again, I have this inside function. And so now I just got to work on taking that derivative there. So again, y prime so far is 1/2 multiplied by sine of 1 plus x squared to the power of negative 1/2 multiplied by this new derivative. Okay, so let's take the derivative of the outside function. The derivative of the new outside function will just be cosine of, remember, the inner function does not change. And this is going to be multiplied by the derivative of the new inside function. Well, the derivative of 1 is 0, but the derivative of x squared, that's 2x. And therefore, we've now accounted for all of the derivatives of all of the function compositions that were taking place here, which means we can now rewrite all of this. When we rewrite all of this, we will have a fraction because, again, we don't want any negative exponents. So let's make sure we tackle that. In the denominator, we will have the square root of sine of 1 plus x squared. Again, that was my square root. Perfect. On my numerator, notice I have a half and a 2, and when they multiply, they will multiply to 1, which means my numerator is left with x times cosine of 1 plus x squared. And there is my derivative. All nice, neat, concise, and more importantly, consolidated and factored. Again, when you're working with the chain rule, it is important to always account for all of the function compositions that are taking place. Let's look at another one. Let's look at part B. So I want to look at part B as f of t, which is going to be equal to t multiplied by sine of pi times t. Okay, so when I'm looking at this, one of the first things that I notice is that I do have multiplication, which means we will be using a chain rule, or sorry, a product rule. I also see that my sine function has an embedded function in its argument, which is not just solely the function t, it's a coefficient times t, which means we have a function composition. So we are going to need the product rule here, and that's one of the first things that I'm going to identify here is we're going to use the product rule. And we're going to take this step by step. So if I want my derivative, f of t, I need to implement the product rule. Well, the product rule says that if you take the derivative of the first function, all right, so the derivative of t, that's just 1, multiplied by the second function, that's sine of pi times t, you add that to the first function, which is just t, times the derivative of the second function. And the derivative of the second function is where we now start having this chain rule process. So far what we did is we used the product rule. That's all we did here, is we used that product rule. Now I'm going to use the chain rule. So I'm going to go through and clean this up just a little bit more before I start using my chain rule. And so far I have sine of pi times t plus t times now the derivative of sine of pi of t. And now is when we want to identify that we do have this outside function. So outside function, and we do also have an inside function. And that's my pi times t. So when I go through and I take this derivative now, I have to account for that chain rule, which means f prime of t is going to be equal to sine of pi times t plus t multiplied by, well, let's take the derivative of the outside function. The derivative of sine is simply cosine, keep the inside function the same, so cosine of pi times t. Then it's going to be multiplied by the derivative of the inside function. Well, the derivative of the inside function Pi is a constant, which means a constant times t, the derivative is just pi. And there we are. All we have to do is clean it up. So let's go through that. F prime of t is equal to sine of pi of t plus, we're going to have pi times t multiplied by cosine of pi times t. And there we are. That is our derivative. We can do nothing else, we can't factor anything else, and we can't combine any more like terms. Which means at the end of the day, this is it. This is all we're looking for. All right, looking pretty good. Let's see if we can try something, again, a little bit more complicated. Because as you can see, we're increasing the difficulty. We started from the previous examples at the very top of your screen just by identifying what was the chain rule. In the next few examples that we did, we then said, okay, well, let's try function composition where we have multiple functions being composed, or multiple embedded functions. And then we said for part B, well, we can do the chain rule, but we can also mix that or combine it with the product rule. Well, let's look at part C. Looking at part C, I want to have y is equal to sine of t plus cosine of the square root of t. Now this function might not look too bad at the beginning. However, once we get into it, we'll see that it's still a lot of function composition that's taking place. And we will always need to account for all of the embedded functions when we take those derivatives. That way we can apply the chain rule. So one of the first things that I do see here is that I kind of want to rewrite it. Anytime I see a square root, I want to rewrite it in a different way. So I'll rewrite this as sine of t plus cosine of t to the power of 1/2, all inside of that sign. And again, now is where I get to see that I do have these inside and outside functions. The first thing that you're going to see is that you do have this big overall function, and that's your sine function. So this is your outside function. And again, this outside function is just sine. Sine, in its argument, has a different function embedded in it. And that's what I'm going to outline, is that my other function, the one that's sitting in the argument for sine, this is my inside function. And again, at first, I don't want to go through and I don't want to identify all of these different embedded functions right away. I want to work with the first two that I identified, and then if I have more derivatives to take, we'll cross that bridge when we get there. So let's go ahead and let's start on y prime. So y prime, the derivative of the outside function, well again, the outside function is just sine. So the derivative of sine is cosine. Remember, outside function, you only take the derivative of the outside and you keep the inside the same. Which means the same, meaning t plus cosine of t to the power of 1/2. That's my first derivative for that outside function. Next, I need the derivative of the inside function. And that one's a little bit more complicated. That one's going to be t plus cosine of t to the power of 1/2. Okay, so we're going to go through and we're going to see, hey, we have some addition taking place here. And because we have an addition, that derivative is now going to be able to take, we're going to be able to take that derivative term by term. So the term that we then need to focus on is this term here. So I'm going to go through and I'm just going to outline that here. That we have y prime is equal to cosine of t plus cosine of t to the power of 1/2. So the derivative of t, that's just going to be 1. So again, that's 1 plus the derivative with respect to t for the function of cosine of t to the power of 1/2. And again, this is where we now see that inside function and outside function come into play. All right, so we're going to identify this now. We're going to identify our innermost function, or sorry, our outermost function. The outermost in this derivative that we're focusing on is cosine. So this is the outside function. Now the inside function is just going to be t to the power of 1/2. So that's the inside function. So now all we have to do is just take those derivatives. And again, it might be easier said than done, but we'll get it done. So cosine of t plus cosine of t to the power of 1/2 multiplied by, we now get 1 plus the derivative of the outside function. Well, that's going to be the derivative of cosine. You know what, let me keep that plus there. So the derivative of that cosine function is going to be negative sine, keeping it the same, of t to the power of 1/2. Actually want that in a different color. There we are. Okay, so good so far. Now we need the derivative of the inside function. So the derivative of the inside function, or the derivative of t to the power of 1/2, we actually did this in the previous section when we were looking at derivatives for different functions. Sorry, and not the previous section. We actually did it in section 2.3, where we were looking at the differentiation formulas. So that derivative, t to the power of 1/2, we know that derivative to then be 1/2 multiplied by t to the power of negative 1/2. And again, that was applying my chain rule to that initial derivative. And now we don't have any more derivatives that we're taking, because when we took that last derivative for the inside function, we took the derivative of the variable t, and that's what we were looking for. All we have to do now is clean this up. So y prime is equal to cosine of t plus cosine of t to the power of 1/2. And then we get 1 minus, and this is going to have a fraction here. So this is going to be 1 over 2 times the square root of t multiplied by sine of t to the power of 1/2. Or we can say square root of t, whichever is fine. And so here's your final answer. That's it. No more derivatives after that point. So again, when we're looking at these derivatives, we always have to make sure to account for all of those different embedded functions. All right. Let's now look at part D. Save the best for last. Again, we want to take this derivative here, and this derivative is going to be y is equal to, or you know what, let's do g. Let's do g of t is equal to t to the power of 4 plus 1 divided by t squared plus 1, all raised to the power of 5. All right. So now again, we have to take these derivatives, or we have to take this derivative, and again, we want to identify that we do have this outer function that we're observing, and we do have this inner function. So the outside function is this whole piece to the power of 5. So that's my outside function. And we also have an inside function, which is that whole fraction, which is t to the 4th plus 1 all divided by t squared plus 1. So if I want to take that derivative, so if I want to take g prime of t, then I need to use my chain rule. So the chain rule says take the derivative of the outside function, so we're going to drop the exponent forward. You keep the inside function the same, and you subtract 1 from the exponent. And now the chain rule says, okay, well then multiply by the derivative of the inside function. Well, the derivative of the inside function, that one's going to be easier said than done. Because now when we look at this, that is now going to involve the quotient rule. So we now need to use the quotient rule here, and I'm going to identify this that we need the quotient rule. So I'm going to say apply the quotient rule. So if we get to apply the quotient rule here, it's going to be quite nice. So let's go through it. Okay, and I'm actually going to work out this quotient rule on the right hand side because I want you all to see this quotient rule. Here we go. So applying this quotient rule, we're going to identify that we have t to the fourth plus 1 divided by t squared plus 1, and I want to take this derivative, which means I have some u and I have some v that I need to account for. All right, so let's account for those. I'm going to say that u is equal to t to the fourth plus 1, which means u prime is going to be 4t cubed. I'm also going to have v, which is t squared plus 1, so v prime will be 2t. There we are. And so when I take this derivative, I need to apply the quotient rule. Quotient rule says we take the derivative of the top function, multiply it by the bottom function, and I'll keep outlining this in just a bit. There we are. So we take the derivative of the top function, and that's 4t cubed, multiply it by the bottom function, which is t squared plus 1, subtract out the derivative of the bottom function, which is 2t, oops, there we go, multiplied by the top function, which is t to the fourth plus 1, all divided by the bottom function squared, which is t squared plus 1. Great. Now let's simplify. All right, so we're going to go through and we're going to simplify here. Remember, you want to simplify as much as possible. So if we simplify as much as possible, let's see. I believe I want to distribute here. And if I distribute, I will get 4t, and I'm trying to see if I want to distribute. Sure, let's try to distribute here. So 4t to the fifth plus 4t cubed minus 2t to the fifth minus 2t, all divided by t squared plus 1 squared. And then I can combine like terms here. So let's keep on combining like terms. I have a t to the fifth and a t to the fifth, so that's going to get me 2t to the fifth. So that's 2t to the fifth plus 4t cubed minus 2t, all divided by t squared plus 1 squared. And I can still factor out a little bit more from that numerator. The numerator, I can factor out a 2t, and what that's going to leave me with is it's going to leave me with t to the fourth plus 2t squared minus 1. Denominator, I still am left with t squared plus 1 quantity squared. Now, I don't believe anything else factors here, so let's go ahead, and this is now my final derivative for that quotient rule. So now I'm going to make that substitution then. So I'm going to make that substitution here. So let's go through. We still have g prime of t is equal to, and I want to keep making sure that I'm using these derivatives, 5 times t to the 4th plus 1 divided by t squared plus 1 to the 4th power. My new derivative here is what we found over there on the right hand side, which is 2t multiplied by t to the 4th plus 2t squared minus 1, all divided by t squared plus 1 squared. And again, we applied the quotient rule there. Now, I can see a few things that can clean up here, so let's go ahead and let's clean them up. So g prime of t. My numerator, I have a 5 and I have a 2, so that's going to get me 10. Let's get this into a good fraction bar here. Okay, so I'm going to have 10t, so that's 10t so far. My first product here is going to be t to the 4th plus 1 raised to the power of 4, then multiplied by this last trinomial, which is t to the 4th plus 2t squared minus 1, all divided by these two quantities of t squared plus 1. The one in orange has a power of 4, but the one in green has a power of 2. Since they're the same base of t squared plus 1, then that means we're going to add them to have an exponent of 6. And this is our final derivative. This is the derivative that we arrive at when we're taking the derivative of that function. And again, we applied the quotient rule, and we also applied the chain rule. Some problems might be of this magnitude, meaning that you are going to have to work through a lot of different components for taking those derivatives in order to arrive at your final answer. So please don't be discouraged by that. Here goes a different example. We're going to say at what point on the curve y is equal to the square root of 1 plus 2x. There we go. Is the tangent line perpendicular to the line 6x plus 2y is equal to 1. And again, now what we're looking at here is, well, we have this point, or we have this curve, y is equal to the square root of 1 plus 2x, and we want to find when is the tangent line to that curve going to be perpendicular to the line 6x plus 2y is equal to 1. Well, we know a few things about slopes. The thing that we know about slopes and their comparisons is that when we arrive at a perpendicular line, we know, or two perpendicular lines, we know that their slopes must be negative reciprocals of one another. So in that sense, I want to then identify what is the slope of this function that was given to us. Well, in order to figure that out, I'm going to start solving for y. As such, and then we're left with y is equal to negative 3x plus 1/2, which means the slope for the line that was given to us is negative 3. But remember, I want the slope of the tangent line, and that needs to be perpendicular to this slope that we found, which then implies that the slope of the tangent line that I'm looking for, and again, I like to denote my slopes of tangent lines with a little capital T, is going to be the negative reciprocal of negative 1/3, which should just simplify to be 1/3. Now I can start taking this derivative. Well, the first thing I'm going to do is I'm going to interpret y as 1 plus 2x to the power of 1/2. And I'm going to speed up the chain rule process. Taking the derivative of the outside function, that's going to be 1/2 multiplied by 1 plus 2x to the power of negative 1/2 after we subtract the 1, multiplied by the derivative of the inside. The derivative of the inside is just going to be 2. 2 times 1/2 will then give me this derivative. So now when I want to find the slope of my tangent line, or at what point, all I need to do is I need to set both of these equal to one another. So the slope of my tangent line, I know the numerical value. However, I don't know at what x value it occurs. However, I do have a general form for the slope of the tangent line to the function y is equal to the square root of 1 plus 2x at any given point. So if I set these two equal to one another, then I'm setting the slope of the tangent line in general equal to one specific value, which is 1/3. So in this sense, I'm taking the slope of the tangent line and equaling it to y prime, which means we get that 1/3 is equal to 1 divided by the square root of 1 plus 2x. We can cross multiply, and we'll get that 3 is equal to the square root of 1 plus 2x. Square both sides, and now we get that 9 is equal to 1 plus 2x. Subtract 1, you get 8. Divide by 2, you get 4, which means x occurs, or in this case, the tangent line that's perpendicular to the line given is going to occur at x is equal to 4. But the question said at what point? So the point is 4 comma, we need a y value. How do we find the y value? Well, we substitute the x value into the original equation. The original equation says that if x is 4, then we have 4 times 2, which is 8, plus 1, which is 9, square root of 9, 3. And there's your answer. At that given point, we will find a line that is perpendicular to 6x plus 2y is equal to 1, where that tangent line will be y is equal, where the tangent line will be tangent to the curve y is equal to the square root of 1 plus 2x. And so that now concludes the lesson on the chain rule. So I hope that you all enjoyed this lesson, and I hope that you all stick around for the next one. And we'll see you then.